Welcome to the UMBC webinar, Engineering a Successful Mission, Lessons from the Lunar Reconnaissance Orbiter. Our guest speaker, Dave Everett, will begin his presentation in 5 minutes. Before he starts, I'd like to give you a 5-minute brief overview of UMBC's graduate programs in Systems Engineering and Engineering Management. These programs are designed by industry experts and are taught by highly experienced practitioners who want to help students prepare for successful careers. They teach very practical courses to give you the skills you need to advance to higher levels of responsibility in your company. One of the advantages of the UMBC programs is their flexibility. You take 4 or 5 required core courses to learn basic skills, and then you have the flexibility to take the remainder of the 10 courses from many choices. The schedule of courses is flexible too. The core courses are taught 2 or 3 times each year, and many courses are 50% online and 50% face-to-face. Our systems engineering program began in 2004 in response to a request from Northrop Grumman for UMBC to create a technically oriented program to teach engineers the fundamentals of systems engineering to accelerate their careers. Usually it takes 10 years or more to learn enough about systems engineering to be in a responsible role in your company. But by learning the fundamentals, you can become a successful systems engineer much sooner. There are 5 different graduate programs at UMBC involving systems engineering. The first is a certificate program in systems engineering that requires 5 core courses in the fundamentals. These same 5 core courses can also be applied to a Master's of Science degree in Systems Engineering, or you can take those same 5 courses and apply them to a Master's of Electrical Engineering or Computer Science, and with a Systems Engineering track. And the final option is to take the 5 core System Engineering courses along with 5 management courses to get a Master's of Science in Engineering Management with a Systems Engineering track. Here are the courses required for the Masters of Science in Systems Engineering. The 5 core courses cover the system engineering life cycle from concept through requirements definition, architecting a successful system, modeling and simulating a system in advance of building it, so that you can be sure the system you're designing will actually do the job, then building, integrating, and testing it. The final core course is a capstone project that uses what you learned in the 4 previous courses. Teams of students choose a complex system to design, model, and simulate. And then the remaining 5 core courses in the master's program can be taken from several different engineering disciplines, depending on the field in which you're working. Looking at the column on the right, the benefits of the UMBC programs are that they fit your career needs and interests. They provide focused knowledge and skills for success in your career. The faculty members are subject matter experts with many years of experience, and the courses are convenient for a work-life balance and to accommodate your travel needs. You can learn most anything you'd like to know about the Systems Engineering program at our website, umbc.edu/SE. Now let's take a quick look at our Engineering Management program. This program combines practical management courses with 4 courses that provide technical depth. Most of the management courses are 50% online and 50% face-to-face, so that for each course you come to campus only 7 times during the semester. You take 4 management courses that apply to either a master's degree or a certificate, 2 elective management courses from a list of 13, and 4 technical courses chosen from 10 technical tracks, including systems engineering and cybersecurity. So the 4 core courses are shown here. 1 of 2 courses in project management. One of these courses is a general project management course, and the other one is aimed specifically at systems engineering. You also take a course in management, leadership, and communication, a course in law and ethics, and 1 of 2 choices in financial management. One of these financial courses deals with company finances, such as cash flow and balance sheets, and one deals with the financial decisions managers need to make, such as investing in new technology or new facilities. In addition to these 4 courses, students take 2 management electives and 4 courses in the technical concentrations that are listed on this next slide. So you can see that the technical courses cover most of the engineering disciplines and information technology disciplines as well, including systems engineering and a new program in cybersecurity. These courses are explained in detail at the engineering management website, which is umbc.edu/engm. If you have any questions about either of these programs, you can ask them during the webinar by typing them in, or you can contact me or the other people listed under Contact Us on the bottom left corner of the web page. And these slides, which I know I presented pretty quickly, and the main presentation too, will be available on both the System Engineering and the Engineering Management website in a few days. Now let's begin the presentation, which I know you're all waiting for, on the Lunar Orbiter. I'd like to introduce Dave Everett, a friend, colleague, and a senior systems engineer at NASA Goddard Space Flight Center. Welcome, David. I'm going to hand the presenter role over to you now. Did I do it?
Hi, Ted. Just wanted to make sure I'm coming through okay. All right, so this is my first webinar, so it's a little different than talking to an audience that I can see. But at any rate, I believe I'm coming through. Maybe, Ted, you can just send me a chat message to make sure that you're seeing everything that you're seeing my screen. Okay. Well, welcome everybody. The first slide here is a picture of our Lunar Reconnaissance Orbiter team, and that's sort of a theme that'll run throughout my presentation. I'm going to flip down through the slides now. I'm going to give you a quick overview. Let me play with my tools here. I've actually got a laser pointer. So I'll give you a quick overview of the moon, maybe some things you don't know about it, and then what LRO is all about, what we've done to date, and then get into some of the aspects of the systems engineering, the environment that we had, and the challenges that we had to overcome. The moon, this is an actual photograph from Mars Odyssey showing how far the Earth and moon are apart. One of the things I like to do for a talk, if you imagine a 12-inch globe on that scale, the moon is the size of a softball, and it's about 30 feet away. So the moon is actually a really long way away. And this kind of gives you a feel for some other things on that same scale. The diameter of the moon is about 27% of the Earth. It turns out the land area is on the order of a quarter of the Earth's land area. That's because the Earth is mostly water. It's more than North America and Europe combined. So it's a pretty big place in terms of surface area. Just a nice shot from 1968, the first time humans got a look at the Earth from the lunar perspective. LRO was started in January of 2004 with an announcement from the President that there was going to be a series of robotic missions to the moon beginning no later than 2008. And this 2008 became a big driver within our design, and I'll talk about that a little more. We we ended up with 6 instruments selected by December of 2004, and started started funding in 2005, still targeting a launch less than 4 years later. And then there was a 7th payload added a little later in the flow. So LRO was all about characterizing landing sites, potential landing sites, looking at the polar regions and understanding what resources might be available. Because of the orientation of the moon relative to the sun, you can actually end up with there are permanently shadowed craters, and in fact LRO and LCROSS, which flew along with LRO, have discovered some water in the craters at the poles. We're also looking at the radiation environment. Before LRO launched in the polar regions, a boulder of this size would have been unknown. LRO's got enough resolution. I'll show you some pictures. This size boulder is no problem at all. We see down, we'll actually have pictures of the rovers now that the astronauts left behind. The instruments from LRO, we've got 2 narrow-angle cameras and a wide-angle camera. The narrow-angle cameras have about 1 meter resolution, 50 meter resolution with the wide-angle camera. Laser altimeter. Notice the blanket across here. I'll talk about that a little later. Diviner is measuring temperatures. It's an infrared instrument. Craters measuring the radiation environment using measuring radiation above and below some plastics that simulate human flesh to model the radiation environment that astronauts would experience. LAMP is an ultraviolet instrument, and LEND is measuring neutrons coming up from the surface. And here's the antenna for our synthetic aperture radar. Just going quickly through some of the results. Crater, this is interesting because you can actually see that we were in, this is before we got into orbit around the moon. We were initially in an elliptical orbit, and we got into a lower and lower orbit where the moon shielded the instrument to some extent from the galactic cosmic rays that were coming in. And you can actually see the variation in altitude of the orbit and the period of the orbit. Diviner has measured temperatures down to 35 degrees above absolute zero in some of the regions, some of the permanently shadowed craters on the moon. The coldest places we've measured in the solar system. The LAMP, one of the interesting things that LAMP has discovered is that the permanently shadowed craters are darker than other parts of the moon under ultraviolet illumination. LAMP actually enables us to see the craters in the dark using ambient starlight to illuminate them. LEND has shown that the neutron absorption, which should correlate with hydrogen concentrations, because the hydrogen's a good absorber of neutrons. So the absence of neutrons is hydrogen concentrations, and in some cases it correlates with permanently shadowed craters, and in other places it doesn't. LOLA has mapped the altitude of the moon across the whole sphere to fairly high resolution. These are just some of the global snapshots. You can see the Aitken Basin on the backside of the moon here. And this is a finer resolution of Sea of Tranquility from LOLA. The narrow angle and wide angle cameras, just to give you a feel, these are both, this is a close-up of the area right at the tip of the arrow here. The whole wide angle or a whole narrow angle image is no bigger than the tail of the arrow here. So here's a composite image from our wide angle camera. If you look down right here, this is the crater Tycho. You can see it labeled there. In the center of that crater, you'll notice there's a little mountain peak in the center of that crater. Here's a picture of that mountain peak with our narrow angle camera, and you'll notice the peak right here. As we zoom in on the picture, there's a boulder there, and this just kind of gives you an idea of the resolution that we've got and the imagery that we've taken. Here's a shot from 1972 of the Apollo landing site after the astronauts had departed. You can actually see the lunar module. The next picture is laid on this one exactly, except the shadows come in from the other direction. So this is taken in 2009 by LRO. Just jumping back and forth, you can see the craters all align here, but the shadows are going opposite directions, and you can actually see the shadow of the lunar lander here. Zooming into 50 kilometers, you can actually see the tracks left behind by the astronauts, a shadow from the flag, and the actual descent stage. And then zooming in even closer, you can actually see individual tracks from the rovers. So these pictures are from just a month or so ago. Mini-RF is a synthetic aperture radar that took some imagery. You can see a rill here where lava flowed at one time. So LRO, we started off with this announcement of opportunity selecting the instruments. Our initial constraints were this 50-kilometer orbit that we're in. We were flying on a Delta II launch vehicle. We eventually changed that. I've got a slide or two explaining that. 14-month mission with a largely single string, and originally targeted the 2008 launch. The 50-kilometer orbit at the moon, it's a very harsh environment because of the the moon is in the sunlight. Any given spot on the moon is in the sunlight for 14 days and then in shadow for 14 days. So the temperature range, this is like minus 240 Fahrenheit to plus 200 something Fahrenheit. The schedule was a huge driver for us, and our customer at headquarters was their credibility was hinging on us pulling off our schedule, and we had our review teams expressing concern with the schedule, and engineers on the team expressing concern with the schedule. And so because of all of that, we made sure that when we did set up the mission, we had a good budget. We had enough money to do the job so that we weren't overly constrained on both money and time. But the real challenge was balancing staying on schedule versus how much risk we were going to take with the development and with the flight. So shortly after we got started, somebody actually got this fortune, and we kind of took it to heart. We paid a lot of attention to the quality of what we were doing, while at the same time we were trying to run hard. So how do you do that? You got to find ways to do things faster without compromising the technical integrity. We had really good team spirit. We had a great time doing this mission, and with that sort of environment, you really can get people to put in a lot of effort. There were times when we had to add more people. We had a launch vehicle change that resulted in some changes where we had to add more people. Designing for parallel development, and I'll show you that a little bit coming up. And And the rest of these I'll talk through in more detail. Just quickly on the launch vehicle change, we had an issue. Basically LRO was half fuel, and if you can imagine trying to spin a raw egg, it's the same kind of deal, trying to spin a spacecraft or trying to spin the rocket with all that liquid fuel. The sloshing of the fuel will affect the stability of the spin on the rocket, and we weren't sure we could we weren't sure we could actually meet all the requirements necessary, and so we went through a process of deciding where we wanted to go with the launch vehicle. We decided within our own capability to switch to a solid rocket motor. Changing launch vehicles was beyond the scope of what we could do, but we did brief our headquarters customer on that. And right at the briefing, our administrator decided to switch us to the expendable launch vehicle, the evolved expendable launch vehicle. It was a bigger launch vehicle, which allowed us to use some surplus components and add a little bit of mass to the system, and also a secondary payload, which became the LCROSS mission. But most importantly, it solved the problem with the nutation time constant, because the ELV doesn't spin, the upper stage doesn't spin like it does on the Delta II. So the mechanical team had to redesign to fit on this new launch vehicle with fuel tanks that were left over from another program. And in the process of doing that, we set the system up so that we could do a modular design. The end result was that our mechanical and thermal teams and even some of the attitude control stuff was behind at the time we hit our preliminary design review in 2006. Looking at the integration, you can see our propulsion module, our avionics deck, everything was set up so that we could do a lot of integration in parallel. And it turned out, there was one point where I was standing there looking at the clean room, and in the clean room we had electrical testing going on in one area. We had technician working on heaters on another piece of the spacecraft on the instrument module. Excuse me. And then in a third clean room we had the propulsion module that was being assembled and blanketed. So we had three separate operations going on all at the same time, and this is one of the things that really helped us get the entire system built in a very short time, was having the parallel operation. We did a lot of early interface tests. Nearly every component that we had to integrate with the spacecraft, we did an interface test ahead of time, or several interface tests. We found issues like with the transponder, where there were signals that were swapped, the polarity was wrong. Despite putting all this stuff in an ICD, we had written down what the interface was supposed to be. People still make mistakes with those. You inherit some heritage hardware from somewhere, and that heritage hardware, sometimes doesn't do exactly what you need it to do, and sometimes those subtle issues don't get spotted until you actually try to hook up the equipment. So the early interface tests easily saved us a lot of time in the end. When we got to the final integration of the system, we only had one interface problem in all the components that we integrated, and it was a transformer reversal. So risk management was another thing that worked really well for for our team. We did, I had monthly meetings with each of our subsystem leads in a one-on-one kind of atmosphere to really, find out what was on their mind and what might be an issue. And there were several issues that we brought, that came up at those meetings that we then dealt with at our monthly risk management meetings at the project level. And the CNDH had a power converter that was coming in late, and that's the command and data handling, the flight computer for the spacecraft. And so we actually ended up building up the spare power card with a lower quality part, and in parallel looked at whether we could fly that part, but it bought us some time while we got the part we wanted to fly in. But none of that would have happened if we hadn't been doing the risk management and talking with folks and understanding what the concerns were. On the procurement side, we did a lot of work, a lot of system support, making sure we had the right environmental requirements, making sure the interfaces were good. We had a manufacturing engineer working with all the vendors, making sure that they understood what our quality requirements were, and actually tailoring our expectations based on what the vendors' typical processes were, rather than trying to force them into some process that we wanted to see. A lot of times the process that they had was good enough. But a big piece in all of this was the focus on the people. We solved a lot of problems very quickly by bringing, our project manager had set up a team where we had a lot of different perspectives. We had people looking at things in different ways, just different ways of approaching problems, and we did a very good job at pulling in those different ideas and hearing from folks. People were willing to speak up on the team, and part of the reason for that, it's really an effort to get people to speak up and say what they want to say. Some people don't want to be a bother, or a lot of times, that somebody might know that there's some little problem, but they don't really see how it will ripple out and impact the rest of the system. One of the things that we struggled quite a bit with is making sure that everybody felt heard. Some people require more effort because they don't match your style, or they have less experience, or you always get the folks who worry too much, and you're constantly hearing from them. Well, what about this? What about this? What about this? And it's easy to start dismissing those people, but in reality, I'd much rather have the people who tell me too much rather than the folks who are worrying about something and don't speak up. And so we tended to we had to respond or at least provide feedback to folks. Even if we decided not to address a particular issue that somebody brought up, we had to provide feedback and explain, okay, we thought about this, we see where there might be a risk, but the project's decided that we're going to take this risk, and here's why. And providing that sort of feedback to folks, you'll get you'll get them to speak up again. If you just if you say, no, forget it, we're not going to worry about that, people won't bring up the next problem. So, one of the nutation time constant problem that we had with the launch vehicle and the fuel tank, that was an issue that came up early on. The propulsion engineer said, gee, there's this problem that we might not be able to figure this out, and we won't know whether it's a problem or not for 6 months. And so we worried a bit about that, and looked at it, and in the end we ended up doing the trade study on the propulsion and ended up switching launch vehicles in order to prevent a problem. A really good example of folks speaking up was with our coarse sun sensor. Our flight computer, our CNDH, was designed to read from our coarse sun sensors. The coarse sun sensors help determine where the sun is in the sky in safe mode so that we can find the sun and get the solar rays pointed at it in order to generate power for the spacecraft. Well, this is one of the basic functionalities of the spacecraft that needs to work from the time we come off the launch vehicle. Well, when the engineers were doing their checkout test, they saw a small discrepancy. It was on the order of a couple of microamps of difference between what the current that they expected to see and the current that they were actually seeing. And they didn't have a good answer for why they had a difference. And it would have been easy to just say, it's just a couple of microamps, let's not worry about that. But they didn't understand the reason for the difference, and so they started digging into it. And I encouraged them to keep digging into it. In the back of my mind, I was thinking, it's just some little calculation error. I'm sure there's no problem with the system. They based this on a previous design, so I'm sure it's fine. And that's sort of what was in the back of my mind, but I didn't say that. What I said to them was, well, keep digging into it and let me know what you find out. And it got to the point where they were using, extra test time on the spacecraft troubleshooting this problem, and our integration team was starting to question whether these guys were wasting our time. And I said, let them go, let them figure this out. They need to figure it out. And in the end, what they found was that there was an error in the design of the circuit that would have prevented the sun sensors from working properly when we got out into full sun. We did the tests just using a light source, and it's not as bright as the full sun. And it turned out that we could very easily have lost the mission right at the beginning if they hadn't found this problem. And because LCROSS was using the same circuits that we were using, they had a similar problem, and they also had to fix their electronics. So it was a fairly easy fix. It took us about a week to correct it. It just involved changing some resistors, but this was a case where that little signal poked up and really told us that there was a big issue. Decision making is another challenge for systems engineering. You've got these multi-parameter decisions. In the space business, you make one little mistake with your design and you can lose the whole mission. So we've got these multi-parameter, high-stakes decisions. Again, using input from multiple people and multiple perspectives. I mean, you can think about it like, you're trying to illuminate a problem. If you're only shining light on it from one direction, there's going to be shadows on the other side. You need the different perspectives. You need the different viewpoints in order to see all the way around and figure out what path to take. So, we would analyze what we could analyze, but at some point, especially with a short schedule, you got to pick a path, use your best judgment and follow that path, unless you hit an obstacle. And there were times when we made a decision, we went down a path of ways and decided that we had made a bad decision, and went back and went down another path. And sure, it takes some time to do that, but it also, I've seen projects chew up a lot of time trying to make a decision. So, you got to strike the balance between the analysis and the judgment in making a decision. But the human mind is very good at taking a whole bunch of inputs and coming up with a solution. We didn't spend a whole lot of time looking for other options if we found one that met schedule, cost, and performance requirements. Optimal solution, outside reviewers would sometimes question whether we had found the optimal solution, and from the perspective of, if it meets the schedule, if it meets the cost, if it meets the performance, don't spend any more effort on it. From that perspective, it was optimal, even though, something might be a little cheaper or work a little bit better. Good enough was all we were looking for. But the review teams, they want to see the careful, exhaustive trade studies and a clear analytic rationale. Most of the time, showing them the parameters that we use to make the decision, showing them the list of considerations that went into the decision was sufficient. So we did run into, several examples, one of them was just sort of a difference of opinion. LRO went with a direct orbit insertion, which means we launched from the Earth. 5 days later, we were at the Moon. We did our orbital burn and got into orbit around the Moon. Other missions, the Grail mission right now is on its way to the Moon. It's taking a much longer time to get there. They got time to check out the spacecraft and get things worked out before they go into orbit. We chose to not go through the trouble of designing for the other environments away from the Moon, dwelling in orbit around the Earth or going elsewhere. It was a decision we made based on the inputs, but there were certainly other opinions on that. And there's a whole bunch of other items I could talk about, but I'll just keep pressing on here. We had, after we, usually, you look at the systems engineering textbooks and you get past your critical design review, everybody's off working in parallel, doing the different pieces, and that's the time when the systems engineers sort of finish up the planning for the system level integration, and there's not much else to do for the systems engineer. Well, in reality, there's all that work going on in parallel, and all kinds of problems pop up, and it's normal. These unforeseeable problems that'll come up during the build phase. And the systems engineers got to be on top of those and assess which ones need a system level decision and which ones can be worked by the subsystem folks. Going down the list, you can kind of read some of these. Each of our instruments had a number of problems. We had things like LAMP had a screw that was too long that damaged their board. Well, LAMP was an exact rebuild of another instrument. And yet, you know, this one had a problem, and the one that's on its way to Pluto, maybe the screw's too long there, but it didn't cause any problems. You know, we had a one component we were buying serial number 239. You know, 238 other units had flown 12 identical transistors in each one. We were buying transistors from the same lot, and we had one fail. You know, why did it fail? Well, it turned out there was a little chunk of aluminum inside there that got manufactured in with the part. Well, how did that happen? How do we know that every other one isn't going to have the same problem? You know, we had to work through those issues. Our transponder had a software glitch that it wouldn't lock up to a 1010 pattern, and we ended up changing how the ground stations operated, so they do a 1100 1100 pattern instead. So there are all these sort of details that come up between CDR and INT. And then finally we got to the point where we were integrating the spacecraft. We did a tabletop integration of most of our avionics. And then after the avionics were integrated, we had the integrated propulsion module and put the whole spacecraft together. Here's the reaction wheels, the real reaction wheels, the propulsion module being built up, and the team that put it together. And then you know, assembled the entire spacecraft with all these different pieces that had been built separately. And then the fully assembled spacecraft, I already walked through this picture, just some different perspectives on it. And then we had the ground system that we built at White Sands also. This is an 18-meter antenna. And then after it's all assembled, you got to do a bunch of testing to make sure it's going to work, because once it launches, you can't get it back. So we do a shock test. Here's the separation system's right in here, and it's holding this ring. We fire the pyros, and boom, it drops off. Testing the electromagnetics, blasting it with radio waves, making sure that radars at the launch site weren't going to interfere with the instrument. We put it in a thermal vacuum chamber and pump out all the air and run it over temperature to make sure everything works hot and works cold, and make sure it can handle the thermal environment at the moon. So then after we went through all the testing, we had to make sure all our paperwork was in place. We had you know, all of our reports and our work orders for all the work that we did, all the problem reports, make sure all the problem reports were closed out. And you know, we didn't close off we didn't check off requirements as being verified until the work orders were closed. The work orders were still open until the problem reports were closed. So this really being very rigorous about making sure all the paperwork was closed, you know, really helped make everybody comfortable that we had taken care of everything we needed to take care of. And then we loaded it all on a truck, drove down to Florida. This is the team that was working on the final checkouts at the launch site. And so you get almost to the end, you know, and this is where some folks get launch fever. You know, okay, it's ready. Let's just get it out. But you know, this is where you don't want to stumble. We had some issues with the launch vehicle that delayed us all the way out till June. We used that extra time to do some additional operations testing and readiness, making sure that we were ready for that lunar orbit insertion burn just 5 days after launch. when you get to the launch site, you get a whole lot of attention from upper level management. Everybody becomes hypervigilant. We find these new problems with the spacecraft, and then when we look more carefully, it's like, well, gee, it's been doing that all along. We just didn't notice it before. And so, these are all just part of the business. And then one of the things for a project that was as schedule focused as we were, to lose control of the schedule at the end because of the launch vehicle and range issues, it's other people are in control of your schedule at that point. And so it's very important to stay flexible, and so there's lots of fun and lots of stress. I tell my kids my job is fun because it's hard. And I think they get that now that they're approaching college. And, it's like video games. You don't play level 1 forever because it gets boring. We put over 3,400 hours on the spacecraft. Here, this is the LCROSS spacecraft, and here's LRO inside the Atlas V fairing. Loaded up onto the rocket. Rolling out. This is the shuttle on the pad, getting ready to launch about the time we were. And then June 18th, 2009, we finally got off the launch pad. And so, looking back, mistakes. We all make mistakes, and the challenge, especially in the space business, is to avoid the fatal ones. But that's true anywhere. We treated mistakes and failures as a normal part of the job. The last thing you want to do is hide some mistakes, and then find them later on when it's a lot more costly. Couple of the things, the complexity of our high gain antenna and the solar array. There was a lot of interplay of a lot of different subsystems, and those pieces ended up needing a lot more systems level attention than we actually had. Contracting issues that came back that we hadn't really fully thought through. And then also, because our schedule got stretched out by the launch vehicle late in the game, a lot of people had put in a lot of time and were very tired. The high performers are the ones that don't always take a break when they should, and don't speak up as well as they should when they're overloaded. We knew that we were overloading people. We knew everybody was getting tired, and so we were trying to be extra vigilant, for the kind of mistakes that would show up because people are tired. So definitely a challenge to make that balance. Failures and flaws. The core sun sensor circuit I talked about a little bit. Our solar array gimbal power was the power dissipation out of the wires. There was an error in the calculations of how much power was being dissipated, and we found that it was actually somebody at a review that pointed out that we had missed a test. We picked it up at the system level, and when we did that test at the system level, we found this particular flaw rather quickly. It wasn't what the reviewer was worried about, but it was a problem that we found because of the extra test we did. We had some problems with one of our instruments with high voltage arcing. Even though we did end up swapping out after testing, we swapped out with the flight spare, and then put some safing on board that helped protect the instrument when the problem happened again. With LOLA, the blanket ended up being a little bit too tight, and everybody was very surprised about this one because it looked like there was enough slack in there, but The alignment was whenever we view a cold part of the moon, the blanket shrinks and it pulls the laser and the receive telescope together, and so the 5 spots of the laser end up sitting in two of the spots actually end up in 2 other spots. So we were actually able to still get a fair amount of data, and it really didn't have a big impact on it. But you know, there's always some problems that you're going to have. Just some observations. There's a book by Daniel Pink called Drive, where he talks about autonomy, mastery, and purpose, and being the big drivers in motivation. And you know, certainly for our team, it was very true. You know, the team members really owned their solutions. The subsystem leads, you know, really felt a lot of ownership for their subsystems, and you know, we gave them a fair amount of ability to make their own decisions and only come to the system level for things that were crossing boundaries. And they really understood that the decisions that they were making, you know, controlled everybody's destiny. You know, we were always challenging folks in constructive ways. As a systems engineer, I use basic physics, and then I expect the experts to explain things to me in those terms, and that works pretty well. You know, headed to the moon was a fun purpose for all of us. Some of the lessons learned, you know, we changed our launch vehicle because we pointed out to our stakeholder, sometimes your stakeholders can relieve your problems. So don't forget to let them know where they could help you. You know, I didn't really talk a lot about this. I'll kind of skip over it just because I'm running out of time. But the overall flow actually worked in our advantage throughout. But even if the schedule's tight, make those sound technical choices. Remember that fortune cookie. The interface tests that we did saved a lot of money. You know, test early and often. The parallel development also helped us a lot, decoupling the delivery events so that you can go in different orders. It didn't matter what order our instruments came in, we could integrate them in different orders. And then really systems engineering is all about the team. The success depends on the whole team. You know, the extra effort it requires to get input from some people is really worth the extra perspectives. Watch out for the overloading, be flexible and optimistic. So I collected a list of all the folks that worked on LRO, and this is the credits list, kind of like you'd run at the end of a movie. So at this point, I believe Ted's going to help pull out some questions.
Yeah, Dave, thanks. That was a fantastic presentation. I've seen it once before, but it helps to see it a second time. So it's really excellent. Just demonstrates superb system engineering and teamwork. We have one particular question, a detailed question, and then there's some general questions also. But the detailed question is, going back to the beginning of your presentation, how was the fuel sloshing problem solved?
We solved the problem by not going on a spinning rocket. You know, initially we were set to fly on a rocket where the upper stage would spin at 60 revolutions per minute, and so the sloshing of the fuel was going to be a problem in that particular case. The tanks are typically set up so that there won't be a lot of slosh in the tanks, but it didn't. Because because we were half liquid, spinning at 60 RPM, the amount of slosh that we were going to get could likely interfere with the launch vehicle, and that was really the whole issue there.
Thanks.
So we solved it by going to a non-spinning launch vehicle.
Yeah, didn't have to solve it the way you initially thought you might have to.
Right.
You certainly demonstrated terrific system engineering skills, but I wonder if you can just sort of summarize what skills does a system engineer do? That, if you've illustrated them, but can you just put it in words? What skills does a system engineer need?
Stand by. I'm just switching you back over. Just switching the presenter right now, and then I'll answer your question. Okay, so what skills does a systems engineer need? Well, certainly you need all of the you need the knowledge base for the type of system you're working on. So you need to have kind of an overview of what all the pieces are that come together for the type of system you're working on, and you need the engineering skills. There's particular capabilities and processes associated with systems engineering, like requirements management and understanding the just the process for pulling the system together. And the program at UMBC and at other colleges is focused on that aspect of it generally, the systems engineering process. But then the other pieces that are really important are leadership skills. Getting the entire team to move in the direction that you need to move, and communication skills. Facilitating communication among people, because systems engineering really is about taking a very complicated problem, breaking it up into a bunch of pieces, and then bringing those pieces back together in the end. But all those pieces go out, and it's a bunch of different people that work on all the different pieces. What makes systems engineering unique is that you're solving a problem that's too big for one individual to solve. You're solving a huge problem that involves lots of people. And I showed you the 1,300 names of the people that worked on LRO. And so the communication skills and the leadership skills are very important. Well,
clearly you have those skills, but I wonder, what was the path that you took from, whatever technical role you started with to becoming a systems engineer?
Yeah, well, I studied electrical engineering, and got a bachelor's and a master's degree in electrical engineering. I worked at Westinghouse for 5 years doing radar receiver design. And so, got exposure to hardware and designing and building hardware, and software. But when I came to NASA, I started out, again, working kind of on radio type equipment, but quickly got involved with, actually I was a test conductor for a spacecraft, which basically meant that I sat in front of a computer terminal, watched the telemetry coming from the spacecraft, and ran procedures that other people developed. I was sort of the single point of contact to the spacecraft, but I really didn't have a lot of expertise with the spacecraft. So I was kind of an operator, and learned how spacecraft work through that process of sitting there and working with the subsystem engineers and sending commands to the spacecraft. So that combined with taking a bunch of classes, I took a bunch of short classes on attitude control and power systems and orbits, and all the different specialties associated with spacecraft systems. So that broadened my experience base, and that combined with the experience that I got working as a test conductor and then as a electrical lead on one spacecraft, and then I was able to expand into systems from there.
So it sounds like you made a leap at some point from individual roles to an leadership role for the whole project. How did you make that transition?
Well, one of the things that helped a lot, we were building small spacecraft here at Goddard, where we had a rapid turnaround, so you had the ability to watch from beginning to end. And as an electrical engineer, in the organization, I was put on as the electrical engineer for this particular spacecraft, and I worked. I was mentored by the spacecraft systems engineer who looked across the whole mission. And so there was a mentoring relationship also that helped bring me up to speed on what needed to be done as a systems engineer. So some of it is just on the job training and working with the right people to really understand what the job entails.
Well, thanks. That's a good explanation for the journey of how you got there. Again, thanks for your excellent presentation. I think the audience must have really enjoyed it the way I did. And members of the audience, I thank you for attending very much, and I hope you enjoyed it and learned something that you can use later. And I'd very much appreciate it if you would take the time to complete the survey so that we can improve these webinars for the future. Remember, the presentation will be available on the System Engineering and the Engineering Management websites in a few days, so you can just visit those to replay this. Thanks again.